In this video, we will talk about optimal foraging, which refers to animals using most efficient strategies in order to gain the most amount of food for the least energy or for whatever other constraints that they have facing them. Recall crows and whelks. So crows dropping whelks on rock surface to actually break the shell and therefore eat the mollusk. Recall also that scientist Reno Zach went out and collected data on the number of drops required to break the shell, and this was the function that modeled that data. So the idea here is to find the optimal height from which the crow should drop the whelk to minimize the amount of work required to break it. So where is that happy medium of the height which will guarantee to break the whelk with the minimal amount of expanded energy on the crow's behalf? So from physical principles, we know that work is proportional to the distance, or in this case, the height that the crow flies. And the total height that the crow flies will depend on the number of drops it actually has to make. So the total height is going to equal to the height of one particular drop, or every drop, times the number of drops in total. Now, here we actually have variables assigned to all of those things. The height of one drop is h, and the number of drops from the height h that the crow is expected to make before the whelk breaks is, of course, described by this function, which is d of h. So the work is proportional to that, which means that up to proportionality constant, I'm trying to minimize the function W equals h dh. The proportionality constant really doesn't have to affect our analysis. Think about this. If you want to maximize 5x, all you have to do is minimize x. The minimum value for x will also correspond to where the minimum for the function 5x occurs. So the proportionality constant will affect the actual amount of work, but it will not affect the height at which the minimal amount of work occurs. Okay, so from here on, once we've set this up, this is just calculus. We have to minimize this function, so we need to find its derivative, we need to classify its critical points, and then see what calculus tools will be useful to apply there. All right, so this is my function, h times dh. So notice that I've taken this and I multiplied it by h to get my work function, and this is its derivative. I'm trying to find the minimum of this function. So first of all, I have to find critical points. Recall that critical points occur when the derivative is either 0 or does not exist. So in this case, my derivative is not one compact function yet because I've taken the derivative of this separately. Derivative of h is 1, and then I applied the quotient rule to the second portion to get the fraction. So I can't here use my really handy analysis of the derivative is 0 when the top is 0 and does not exist when the bottom is 0, because this is not one fraction in total, right? So I'm going to have to work on it a little bit. So does not exist actually proves to be the easier thing to analyze here. So my derivative does not exist when there are numbers that I cannot plug in. And of course, because there's a denominator, and we've sketched, this function before, it has a vertical asymptote at 0.84. I know that it doesn't exist when some bottom of that fraction is 0. So in this case, when h is 0.84, the derivative is equal to 0. This will require a little bit more algebra because I actually have to set this entire thing to be 0. I encourage you to pause here and think about how you would do it. So I'm going to write one step in here. In setting this to be 0, I've separated the two pieces. I can then cross multiply, square root both sides, get my h value, and so the h value that comes out to be the solution here will be 4.8998. And of course, this is in meters. So we have two critical points, 0.84 and 4.98. This isn't quite a point, it's an asymptote, but we can run first derivative analysis, or we can take a second derivative of this function and run a second derivative test on our critical points in order to determine whether they give us the global minimum. The other way to do it is, of course, to test out the endpoints, and that's the method I'm going to use, but I encourage you to do the other two methods just for practice. So in terms of endpoints, I have to think of what is the smallest and the largest that this h can be. Well, right in the problem in itself, I'm given the restriction that h has to be bigger than 0.84, so my smallest point is 0.84, except for we know that that is a vertical asymptote for all of our functions here. So I cannot plug in 0.84, but I can plug in a value really, really close to it in the limit. So I'm going to take a limit as h goes to 0.84 of the function that I'm trying to minimize, which is w. So I know that if I plug in 0.84 here, I'm going to get, or limit, sorry, if I compute limit at 0.84 here, I'm going to essentially get 0 on the bottom. And overall, my limit then will go to infinity. It's a vertical asymptote. That makes perfect sense. The other end of the spectrum, I have to think of what is the largest possible value that h can have. So what is the highest possible height from which the crow can drop its whelk? Well, I'm not sure exactly how high the crows will fly, but mathematically, once again, because there's only two critical points to consider, I can think of that as being infinity. Okay, you can plug in just a very large number that you found out is the limit of the bird's ceiling sort of thing, but without having to do any research into the maximum height that a crow can fly, I can compute the limit at infinity here. And again, I'm computing the limit of this function, my actual function that I'm plugging it back into. This will go to infinity and this will go to 1. So overall, my limit will be infinity, which is really not that surprising, right? Neither of these things are terribly surprising. If the crow is to drop the whelk from the minimum possible height of just under a meter, it will probably take it forever to break the whelk because the height is just not enough to create the amount of force required to break the shell. Whereas if the crow flies up into the space, let's say it stays in the atmosphere or it pretends to be a Baumgartner, it will probably have to only fly once, but it will take an unlimited amount of energy in order to be able to reach that height. So the fact that both of these limits are infinity makes perfect sense in the context of the problem. Now, to analyze which one gives us the global maximum, we simply compare the critical points that we had with our endpoints. So we compare these three numbers to find the smallest one. And of course, the smallest one is the one critical point that is an actual point. And this turns out to be the global minimum. Remember when we first introduced this problem, I told you that the whole reason behind this investigation by the biologists was the fact that they noticed that crows somewhat uniformly drop whelks from the height of about 5 meters, and we set off on the investigation of why that is the case. Well, turns out that approximately 5 meters is exactly the height that minimizes the amount of work that is required to break the shell. The conclusion here, of course, is therefore crows know calculus. Optimal foraging, which are strategies that animals employ in order to gather food most effectively. Our first example, we will consider a honeybee, and hopefully that is something you've actually witnessed in real life. A honeybee collects nectar from a flower, and then once the nectar gets depleted in that particular flower, or just maybe when it feels like it, the bee will move on to the next flower for further collection. Of course, once it decides to switch flowers, it has to travel to another flower, and therefore there's a period of time when it is unable to collect anything at all. So the bee is faced with a decision to make. When should it leave a certain flower? At what point in the collection should she decide that there's simply not enough nectar on this particular flower anymore, and it's worth the time investment to look for another flower in hopes of finding one quickly and beginning the faster collection rate? So with that in mind, what does bee actually want to maximize? In the end, it wants to maximize the total amount of nectar that it actually collects. However, we need to account for the time that it takes to travel to another flower as well. So in the end, it's not just the total amount of nectar that we want to maximize. We actually want to maximize the total nectar intake per visit, including travel time. Now, if we're thinking about the total amount of nectar, first of all, we're going to have to set this function up, this objective function up in a couple of steps. Let's first think about just the total amount of nectar intake per visit if the bee stays on a flower for some time t. What do we expect that to look like? We expect the collection rate to be pretty high at first because there's still a lot of nectar available. But a flower only has so much nectar to offer. So in the end, we expect that the bee's collection rate will slow down as the nectar gets depleted. So maybe take a second here and try to sketch what you expect this function to actually look like. Time versus the amount of nectar. You should get something like this, where at the beginning, the rate of collection is fast, and then it plateaus out. Now, of course, this looks fairly familiar. This shape we should recognize by now as a linear hill function. Notice that if we expect high collection rate at first, it should really be a linear hill function that we're sketching. Just for an example, let's take this function, which describes total amount of nectar, to be a very simple hill function. So t over t plus 1. Now, as we've mentioned before, it's not the total amount of nectar that I'm trying to maximize. I'm trying to maximize, me being a bee, I'm trying to maximize the total amount of nectar per visit, and that has to include the travel time because I have to factor that in when I decide to stay on the flower or leave the flower. So this R of t will be the rate of nectar collection after t minutes on the flower. So not the total amount of nectar, but rather how fast, or like what is the proportion with respect to time. Okay, so I'm also given that for this particular patch, I have 4 seconds of travel time between every 2 flowers. What I really have is that RT is the total nectar amount per visit divided by the total time per visit. Now, the total time per visit will consist, of course, of 2 things. The total amount of time that the bee spends on the flower, and then the travel time to reach the next flower. So there's 2 things here, time on flower and travel time. Now, luckily, we actually have both of those described to us as already known quantities, or at least identified quantities. The time on flower is exactly t. This should actually say seconds. So the time on flower is t, and the travel time is given to us as 4 seconds. So the total time per visit is t seconds on the flower, and then 4 seconds to travel to the new flower. We also know that the top here, the total nectar per visit, is exactly what this function f is describing. So this is my function f of t. So altogether, I have f of t over t plus 4, and I know that my f of t is this linear hill function t over t plus 1, so I can plug it in, combine denominators, and I'm going to get t over t plus 1, t plus 4. Now that we have this function, we know that this is what we would like to maximize. So our objective here is to maximize R of t. And what domain are we going to consider it on? What is the shortest amount of time that a bee can stay in a flower? Well, 0. What is the longest? Realistically, probably bee's lifespan, but mathematically, we can simply analyze it to be infinity. So we would like to maximize R of t on the domain from 0 to infinity.
Now, all that is left to do is pull out our calculus tools and actually work with this function on this domain to find the maximum. We are here, of course, after the global maximum. So as always, there's a number of ways to proceed, but no matter which way you pick, you're going to have to first compute the derivative of this function and maybe possibly a second derivative, depending on which route you take. So here's the exact same function. And here is its derivative. I've already computed it for us. And we would like to maximize it on the appropriate domain. So remember, I had that t is greater than 0, from 0 all the way to infinity. So the first things I have to do here is to figure out what are my critical points. Okay, so as usual, critical points is where the derivative is equal to 0 or where the derivative does not exist. And I will have an easy case here because, as in several examples before, I have one big fraction, which means that I can separate these cases into the derivative being 0 is the fraction being 0, which only happens when the top is 0, and the derivative not existing corresponds to the entire fraction not existing, which occurs when the bottom is 0. Okay, so for the top equals 0, what do we have? We have that 4 minus t squared has to equal to 0. And if we solve for t, we're going to get plus or minus 2. Now remember that our domain is t is bigger than 0, which of course means that negative 2 is not admissible because it's not in the domain, which means that the first case yields one critical point, and that is t equals 2. This is our one critical point coming from here. And let's see if we have any other ones coming from the non-existence case. So the bottom is 0, means that either one of these brackets has to be 0. So if the first bracket is 0 here, I'm going to get that t is equal to -1, which of course is not in the domain. And the second bracket here will yield t is equal to -4, which of course also is not in the domain. So both of these are in fact going to be not considered for the exact same reason. So that means that I end up with only one critical point, and that is t equals 2. Again, there's a number of ways to proceed. You can do the second derivative test, take a second derivative of this function or the first derivative of this one, and then analyze whether it's positive or negative for this particular point. I know that my domain starts at 0, goes towards infinity, so I'm actually just going to use the first derivative test and then confirm it using the endpoints. Okay, so let's say I want to use the first derivative test and confirm what's happening using the endpoints. So the first derivative test means that I do have to look at my number line. I'm going to put all of my critical points on the number line. All of them means really just this one, t equals 2. And then I have to analyze my function before and after 2, whether its derivative is positive or negative, and that will lead me to conclude whether the function is increasing or decreasing. So if I pick a number here between really 0 and 2, because that's where my domain starts, and I put that into the derivative, I will see that I'm going to get a positive number first, which means that my function is increasing. And then if I pick a number bigger than 2, put it into the derivative, notice that the bottom is always positive. So I'm really only plugging numbers in into the top. So if I plug in, let's say 100 into the top, I can easily see even by using mental calculations that the top is going to be negative. So the entire derivative is negative, which means that the entire function is going to be decreasing. So that means that 2 is a local maximum, and I need to do some further analysis to conclude whether or not it's the global maximum as well. Okay, we're going to need a little bit more space here. So my next point of analysis is going to be thinking about the endpoints. So what were my endpoints? My endpoints were 0. My endpoint was infinity, really. And then I also have to plug in my critical point because I would like to compare the values for the global maximum. Okay, so these are my endpoints, and the critical points is just my number 2. So I'm going to plug them in the function itself to actually figure out the amount of nectar. So plugging in 0, plugging in infinity, I can't plug in infinity, I have to plug it into the limit. So as t goes to infinity of my function is what I'm going to have to consider. And then I'm going to plug in the value 2. Okay, so remember that when we're looking for global minimum or maximum, we're plugging it into our function itself. So our function is this one here, not the derivative anymore, but the function itself. Okay, so if I plug in 0, I'm going to get a 0. What happens if I plug in infinity? So let's take a look here. If I am calculating the limit as t goes to infinity of this value, on top my degree is 1, I just have t, and on the bottom, if I open up the brackets, I see that the highest degree is going to be t squared overall, right? There is 1t from here and 1t from there. So using the power analysis, the limit of this function as t goes to infinity will turn out to be 0. So far, both of these numbers are 0, and if I plug in 2, my number is going to come out to be 2 over 18. And comparing these three numbers together, I am interested in the global maximum, so I'm going to pick the largest one, which is of course this one, which means that this corresponds to the global maximum indeed. So that means that in our case, the optimal time for the bee to stay on the flower in order to collect the most nectar is 2 seconds. To stay on the flower. Now, this, of course, depends on all the kinds of assumptions that we've made. In particular, remember that in our function, let me rewrite this here once more, I have t over t plus 1 and t plus 4. Some of the assumptions that we made on our data is that it takes 4 seconds to get to a new flower. And this is where this 4 actually came from, right? So this 4 is 4 seconds of travel time to get to the new flower. So let's think a little bit here for a second. What happens if the travel time gets bigger? So what if the next flower is even further out? What if travel gets longer? So for example, what if it takes 9 seconds to travel to the new flower? What if it takes 10 seconds and so on, right? What kind of behavior are we going to see from the bee if the travel time increases? So what if it takes, let's say, 9 seconds to think concretely to find a new flower? So for example, the patch isn't as densely populated. Okay, so pause the video here for a second and try to think about our analysis and how we went through it to see how changing this 4 to a 9 will affect our entire analysis and our conclusion. Pause here, come back to talk through this together. Okay, so if we replace 4 here by a 9, you will notice that in the calculations for the critical points above, this 4 will also be replaced by a 9 in the derivative, which means that I will be now looking at square root of 9, so 3 all the way through. So nothing else really changes. The bottom analysis doesn't change because it still doesn't yield any critical points. All that happens is that the value of my critical point is going to increase, which means that in here, again, endpoints don't change, but the value of the critical point will increase, and therefore the optimal time to stay on the flower will be longer. Instead of 2 seconds, we're going to get 3 seconds. And in fact, in this setup, if the travel time is some constant a, then the optimal amount of time to stay on the flower is going to be square root of a. The bigger the travel time, the longer the bee will stay on a certain flower. That makes sense, because think about this. If the bee is actually already on the flower and the next flower is really quite far away, it makes sense that staying will produce more nectar as you're collecting than abandoning the flower and traveling for a very long time to find a new one. The further the next flower is, the longer the bee is going to stay on the one that it has. And once again, nature confirms that that is the actual behavior of the bees. And so, as the normal conclusion we draw in this class, bees also have an intuitive understanding of calculus. We're now going to take a look at what is called logistic growth. So this is the type of growth that is what we call density-dependent growth. If you think about how populations grow in the wild, you will soon realize that they very rarely grow at a constant rate. So for example, if you start with 100 individuals and the population, let's say, grows at 20% rate, that means that every unit of time I expect 20% of the original to appear in the population. However, it becomes very clear very quickly that the growth rate of the population depends on other things as well, not just how many individuals there are in the population. Individuals also have to compete for resources, nesting sites, mates, and food. And so the more individuals we have, the less growth rate we are expecting to potentially experience. So these types of models are called density-dependent growth, and the most common among all of them is the logistic growth. So that is given to us by the formula, where G of n here is the rate of growth of the population. What I have on the right-hand side is a bunch of different constants. Okay, so n here is actually population density. R and K are going to be other constants that describe the population. So R and K are positive constants. We will see later on in this course, and certainly in Math 118, if you take Math 118, more examples of analysis of the logistic growth. In particular, R is what we call intrinsic birth rate, and K is what we call carrying capacity of the population. So the maximum number of individuals the population can reach, given its resources, its food availability, and the number of available mates. So let's see what we are trying to do within this question though. We are first of all asked to find the population density n that leads to maximal growth rate. Okay, so for how many individuals, how dense does the population have to be that it grows the fastest it will ever grow? Secondly, we're asked to find the actual value for this growth. And then finally, what population size produces the growth rate of 0? So no additional individuals being born. You already have all the tools to approach this problem, so I recommend you pause here and try to do this for yourself. This question, however, has a lot of constants, so you might struggle a little bit in the beginning through the actual algebra. Pause at any point in the solution to try the next step for yourself before you see me go through that. So for part 1 here, we're asked to find the population density that maximizes the actual growth rate. Okay, so all we need to do is find the maximum of this function in terms of n. Okay, so the one thing that is very important to remember is that n is our variable and everything else is a constant. So I know that this expression looks very bulky, and so maybe we can simplify it before working with it to better understand what it actually is. Okay, so first what I'm going to do is inside the brackets, I'm actually going to split this fraction up. Okay, so k over k is going to be 1, and then I'm going to have n over k left over. Okay, and once I've done that, I'm actually just going to open up the brackets. So first I'm going to have Rn minus, and then again, remember that n is my variable, so I'm going to try to collect n terms and leave everything else as a constant. So multiplying Rn by n over k will give me r over k as a constant and n squared as the other remaining variable portion. R over k, n squared. And now it's not so scary anymore because, again, variable being n, that means that I'm looking at the parabola facing downwards as my overall function that I'm trying to find the maximum of. So I even can use pre-calculus tools at this point because if this is just a parabola facing down, I know exactly where the maximum will occur. I can find the vertex of the parabola and be done with it. But let's apply calculus tools just for extra practice with taking derivatives involving a lot of the constants and general letters. So the first things that I'm going to do, of course, is take a derivative because no matter what way I choose to proceed, I'm going to have to find me the critical points. So taking the derivative of the simplified expression here, and again, remembering that n is my only variable, I'm going to have r minus 2r over k times n. Okay, that's my derivative. Excellent. I am after critical points. So I need to think about when my derivative is equal to 0 and when my derivative does not exist. So in terms of when is it equal to 0, I'm going to take this expression and set it equal to 0. Remember that r and k are positive constants, so they cannot themselves be 0, so that I can cancel them out as I see fit. I can't do the same thing with n because n is my variable and can actually be 0, but with the constants I can do that. So what I'm going to do with this expression, of course, is let's say I'm going to take this and move it over to the right-hand side, trying to isolate n. I can simplify this a little bit here by just rewriting this as the equality this way. I can then see that, yeah, I can divide both sides by r, because again, it's a positive constant, not 0, so I'm not doing anything illegal. And once I've done that, I can isolate n by dividing both sides by 2 over k, and that will involve flipping it on the left-hand side. So I'm going to end up with n being equal to k over 2. Don't just take my word for it, actually go through the algebra to make sure that you get this expression. So this is my one critical point, and then I also have to consider the case of when does this function not exist. Well, I can see that my only potential problem is this k in the denominator, but k being 0 is not in the domain, which means that overall, this case produces no solutions. So I have only one critical point, and that is k over 2. Excellent. Now again, there's a number of ways to proceed. Let's do the second derivative test here, just to spice things up a little bit. Okay, so for the second derivative test, I'm going to need to calculate the second derivative of my function. And for that, I'm going to look at my first derivative and take a derivative of that. Again, keeping in mind that n is my variable. So r is a constant, that will go away entirely. And what I'm going to end up with is 2r over k. The second derivative test says that I have to take my critical point, plug it into my second derivative to see whether the value at that point of the second derivative is positive or negative. But here, I don't even have to do that. There's no n present here, so there's nowhere to plug this in. And that's, of course, because this is always negative. R and k are always positive, and this negative sign in the front guarantees that this expression is always negative, which again isn't really that surprising because we know that this is a parabola facing down, so it's always concave down. The second derivative is always negative for this shape. That also means, though, because it's always concave down, the only critical point has to be at the top of that parabola, and therefore has to be not just a local, but a global maximum. Okay, so let's make sure that we write out that justification in full. So function is always concave down on its entire domain is another thing that you can write here. So the only critical point is global max. Right? Again, thinking about the shape that it is, the only critical point has to be at the top of that hill. Perfect. So that means that we're actually done with part 1. We found the population density, it's k over 2, that leads to the maximum growth rate. Okay, so the maximum growth rate occurs for the population density equaling k over 2. Again, thinking a little bit ahead, knowing that k stands for carrying capacity, the most that the population can be in size, this means that it grows the fastest at exactly half of that. And this behavior is in fact very similar to that of hill functions, where the fastest growth actually occurs halfway between the 0 and the horizontal asymptote. Now, part 2 of the question asks to find the value of the maximal growth at that point. Okay, so now I know that my fastest growth rate occurs at k over 2. We need to find out what g is at this point. So all we're going to do is take n equals k over 2 and plug it in for n in this entire expression. okay? And then simplify. So again, pause the video here. There's nothing here that you cannot do, and actually go through the algebra. So for me here, I am going to say that we need to plug in n equals k over 2 into the expression for g of n. So overall, we're going to have that g of k over 2. Let me move this down a little bit, plugging it in very carefully. I don't have the expression on the same page anymore, but you do. I'm going to have r times n, but now my n is k over 2. So k over 2. And then it depends if you want to plug it into the simplified version or the earlier one. I'm going to plug it into the earlier one. So it was k minus n, and now n is k over 2, divided by k. All right, so this is, again, a little bit bulky, but nothing that we cannot simplify. So let's see here. Outside, we have r times k over 2. Let's leave it as this. What do we have on the inside? An apple minus half an apple is half an apple. So here we have k over 2, all divided by k. Okay, and these two are actually going to cancel. So on the inside of the bracket here, we're going to get 1/2, and multiplying by all of this will yield rk divided by 4. Okay, again, we can interpret this once we actually start thinking in more details about the model, but for now, this is as far as we can take it. Okay, and part 3 of the question, let's go back to see what it asks. For what population size is the growth rate 0? No calculus involved. All we need to figure out is when this thing is actually equal to 0 in terms of the population size, so in terms of n. Okay, so I'm going to take that and I'm going to set it to be 0. So first, let's maybe rephrase it. So we need to find n for which g of n is equal to 0. And again, please feel free to actually pause the video and do this for yourself. This is really great practice with solving equations that consist of no numbers at all. So the left-hand side here is my g of n, the simplified version. The right-hand side is 0. That's what I want. Again, remember, I'm trying to solve for n. Okay, so having a product is always great because the product of two numbers is equal to 0 only if one of these things is 0. So here, remembering that r cannot be 0, it means that this can only be 0 if n is 0. Okay, when the population is at 0, the rate of growth is also at 0. So let's write that down. When population density is 0, so there's no individuals at all, then of course they cannot grow. So this is one of those trivial cases. The rate of growth is also 0. But it is something that we have to still solve for to make sure that we are not missing out on this obvious yet important case. And the second one is when this bracket is 0. So I have that 1 minus n over k is equal to 0. And remember, I'm solving for n. I can move this around and I will see that the solution comes when n is equal to k. So remember what I said, k actually stands for carrying capacity, and this means that the growth rate is once again 0 at carrying capacity. So once the population has reached this value of k, it can no longer grow. Its growth rate is then once again equal to 0. Okay, so when population reaches k, or size k, or density k, the rate of growth is once again 0. And at this point, it's because it runs into the opposite problem. Here, there's not enough individuals, well, there's no one to reproduce or do anything. Here, the number of individuals in the population is too high to support any more. The resources are so scarce that the rate of growth is now at 0. The population, as is fighting for survival and not for growing or reproducing. Okay, so these are the two important cases that we're going to see with these density-dependent growths here and in logistic growth and in other density-dependent growth models.